Hello everyone, welcome to this lecture on analysis of logic gates. Before entering into the detailed analysis of the circuit that is made using the logic gates, now let us discuss in detail about the working of the logic gates with respect to the logic operations that we have discussed in the last lecture. So this slide shows the summary of the basic gates truth table. If we start from the top left corner, we can see the truth table of AND gate, and the immediate bottom XOR gate is given, and the top right OR gate is given, and NOT gate is given. So in these truth tables, we can understand that whenever a logic 0 is given, meaning that it is false or off condition. Whenever logic 1 or 1 is given, it is true or on condition. Here capital I suffix 0 and capital I suffix 1 represents the inputs of the logic gates, and capital I also represents the inputs of the logic gates. So the output function is represented using the logic gate name. So for the single input, we will have two input combinations based on the formula 2 power n, where n is the number of inputs of an logic gate. If n equal to 1, we will have two inputs, that is 0 or 1. If the number of input is increased from 1 to 2, we will have 2 power 2 input combinations. So our 2 power 2 input combinations, as per the LSP to MSB rule, we can have the values ranging from 0 to 3 input range. So the 0 to 3 can be represented in digital form as 00, 01, 10, 11, where 00 is equated to the weight 0, where 01 is equated to the weight 1, and 10 is equated to the weight 2, and 11 is equated to the weight 3. So based on this a small brief introduction about these zeros and ones, how the truth table is written, we'll move forward to the next gate. So we'll be discussing about the concept of digital signals with respect to the logic gates, and we'll be discussing about each and every gate. That is NOT gate, which can also be called as inverter, AND gate, OR gate, NAND gate, NOR gate, XOR gate. First we'll discuss about digital signals. Digital signals means it has two states. One is false or logic 0, another one is true or logic 1. So here the digital signals, one is represented by a small voltage in the signal representation, and the digital signal 0 is represented by a no voltage or 0 voltage. So with respect to the above definitions, now we will see the digital waveform. So here each column represents a small, that is the base of the each column available in this box. So which has 8 boxes, 8 small number of boxes. We can also consider this as a register. So each box is capable of holding 1 bit. So it is like an 8-bit register. So here each column base is represents a small voltage level starting from 0 to 1. So now we can see the waveform representation within this box. So if we look at the voltage levels, the base is equated to 0 or 0 voltage. The top is equated to the logic 1 or 3 voltage. So the voltage range is from 0 voltage to 3 voltage. Here 0 voltage means no voltage, where the digital signal 0 is represented. 3 voltage means small voltage, where digital signal 1 is represented. So if we code this waveform, it can be written as 100, 10, 110. So which is now displaying over this waveform. Now let's look at the NOT gate. So here we can see the inverter gate symbol diagram. So it is similar to diode. We will be replacing the cathode by a bubble. So a logic gate that changes its input logic level to the opposite stage. That is the basic operation behind this inverter gate. So now we will discuss in detail. So now we have the inverter gate. So with respect to the truth table, we'll be forming the truth table based on this logic. So a truth table means a table listing all possible inputs to a circuit and the corresponding outputs. This is the basic definition of a truth table. So now for this NOT gate or inverter gate, it has one input and one output. So the input is marked as A, capital A. The output is marked as Y, capital Y. So now we have to form this truth table based on the input. Since it is a single input gate, the inputs can be of two combinations, either 0 or 1. When we apply 0, the output is complementary of its input, that is 1. When we apply 1, the output is equal to 0. That also we can see it as animation. When you apply 1, the output is equal to 0. Next we will discuss about another gate, AND gate. Here the AND gate symbol is shown. Here we have taken a 2 input AND gate. For the 2 input AND gate, the inputs are considered as A, B, and the output is considered as Y. So now we have to form the truth table for this 2 input AND gate. When the inputs are 0, 0, the output is 0 as per the logic operation of AND gate. We know the logic operation of AND gate. The AND gate produces output equal to 1 when all the inputs are equal to 1. Otherwise the output is equal to 0. So we can also see each and every input combination in animation. When 0, 0 is applied, the output is also 0. Next, when 0, 1 is applied, the output is 0. Because when all the inputs are 1, the output is equal to 1. Otherwise the output is equal to 0. Now we will look another 2 combinations also with respect to the animations. 0, 1, the output is 0. 1, 0, the output is 0. Now 1, 1, when 1, 1 is applied, the output is 1. So this is about AND gate. Next we will discuss about the OR gate. OR gate also minimum of 2 input and we have 1 output. Inputs are marked as capital A, B and output is marked as capital Y. Here the OR gate logic operation is whenever at least one of the input is 1, the output is equal to Y. Otherwise the output is equal to 0. So based on this we can form the truth table for this OR gate. When 0, 0 is applied, the output is equal to 0. When 0, 1 is applied, the output is equal to 1. When 1, 0 is applied, the output is equal to 1. When 1, 1 is applied, the output is equal to 1. So that's about OR gate. Next we will discuss about NAND gate. So NAND gate is the combination of AND and inverter. So the AND gate output is inverter. That is the actual meaning. So we all know that AND gate produces output 1 when both the inputs are 1. Here the operation is just inverse. Now we'll see the operation with respect to the truth table. Here the inputs are capital A, B and the output is Y. When 0, 0 is applied, the output is equal to 1. When 0, 1 is applied, the output is equal to 1. When 1, 0 is applied, the output is equal to 1. Finally, when 1, 1 is applied, the output is equal to 0. So next is NOR gate. Similar to NAND gate, the inverted operation of OR gate is NOR gate. Inputs are A, B, capital A, B, output is Y. When 0, 0 is applied, the output is 1. When 0, 1 is applied, my output is 0. When the 1, 0 is applied, my output is equal to 0. When finally 1, 1 is applied, my output is equal to 0. Next, exclusive OR gate. This exclusive OR gate logic is, as we already discussed, when the inputs are not equal, the output is equal to 1. So here inputs are marked as capital A, B, the output is Y. 0, 0 means the output is equal to 0. 0, 1 means the output is equal to 1. When 1, 0 means the output is equal to 1. When 1, 1 means the output is equal to 0.